what is our job here? First of all, we have to cut costs. So we have to design a new launch platform. This is what we will do next week. Yeah, economists are doing engineering stuff. It will be fun. And increase the demand for the new launch platform. So the simulation behaves like that if you are able to cut costs, then the market is growing for you. So our launch number will increase if we are more cost competitive. Also, we have to solve partial rapid reusability, so at least we have to recover the first stage somehow. Okay, from economist point of view, we have to build up something which is able to land. From engine point of view, it has to be able to throttle down, so it's not just running at 70% of the performance and 100% of the performance, but it has to be able to slow down itself gradually, so you have to be able to throttle down to 40% of the whole power. Otherwise, it would be highly bumpy landing. So, but what we can do here, that we will choose from already existing engines which are capable to do this. Also, what will be important for us is to choose the right fuel. But practically fuel, on the other hand, they are quite a marginal cost. So the fueling up a Falcon 9, it costs less than one, or now it's more than 100,000 US dollars. 100,000 US dollars, okay, it's a lot of money, but compared to the price of the vehicle, it's quite negligible. And also, this is for kerosene, but okay, liquid hydrogen can be much more expensive because you have to cool it down to really low temperatures, and also it's tried to get away in many different ways. So that's why hydrogen is not so welcome nowadays, because it has a lot of problems. Liquid methane, which is natural gas just under higher pressure, nowadays it's really popular because it contains less pollutants, so you can reuse the engines way easier because it will be not it's like that here and there, and it's also quite cheap. And liquid oxygen, it just requires electricity, so you don't have to purchase it from anywhere. Just you need a plant which can manufacture oxygen for you, liquid oxygen, or just using electricity. So so this is the partial reusability. First stage is coming back, land somewhere, it's good for us. Rapid reusability is, that's why we have to make the difference, because Space Shuttle was also reused just between two flights. They had to take it to pieces and after that put back together, so it was taking more than a year, or sometimes it was more than half a year, but so it was limiting the launch numbers. What we can see in the case of SpaceX nowadays, that after a month they can launch the same first stage again and again. So sometimes they have only 10 first stages and they are just rotating them, bring them back into business. So this is the rapid. So it's not like landing and putting the stuff on the top and launching again. That would be good, but first we have to reach this state. And also we are only focusing on cargo. So nobody cares about humans. They are needy. So obviously several G's must. So we have to limit the acceleration, and also they need safety. So we are just focusing on cargo transportation, no humans. Okay, so if you are thinking it from economist point of view, then this is the direction we would like to go. And usually this is the cost structure of the vehicle. So obviously we need some engines on the bottom. So its usually price range is somewhere between 10 to 20 million US dollars. There will be precise prices later, just we have to see that, okay, what is here and what. First stage. So this is what is doing the heavy lifting duty, literally. So in this case, we can see that 75% of the costs are related to the first stage. So that's why we have to recover this. And that's also quite or relatively easy because they are ejected at lower heights. So it's only ejected at 70 kilometers usually, and after that, okay, it's heating up to 100, and after that, it's falling back. But so the speed is not that enormous. So it's not orbital speed; it's suborbital speed because it's coming back without any kind of help. If you can land propulsively, so if you are able to burn again the engines to slow it down, and after that you are able to use the engines again to not to hit the ground, but slow it down again and to land on its feet, then it can be recovered. Also, in the first stage, we need fuel and oxidizer tanks. So we need fuel, we need oxidizer, so it's usually oxygen, and the entire chassis or hull can be made from aluminium lithium alloy or from carbon composite. Obviously, most of them are quite expensive, but aluminum is still cheaper than carbon composite. So carbon composite is really light, but only one company, or now it's two companies, are using carbon. One is Rocket Lab, the other is Firefly. So because you need a special robot to build this thing up, so it's somewhere between sewing and gluing together stuff. So it's not like aluminium when you can get the aluminium sheets and after that you can weld them together, and it still requires some specialized equipment. But in the case of carbon composite, it's like building a boat. Or so you need a shape, and after that you have to put everything on it, and using some epoxy glue to put them together. So Rocket Lab has its own robot to do this. So they are somewhere between 3D printing and additive manufacturing, but yeah. So, and of course, the third option would be the crazy one. So using stainless steel, because this is the cheapest solution, and also stainless steel is quite or remains rigid and structurally stable under high temperatures as well. Just it's heavier than aluminium or carbon composite, so there is a reason why only two companies are working with steel. One is SpaceX with their Starship, which will fly within a month in one or other direction, but we will see that what will happen. So this will be the new launch platform. And the other one is a newcomer, which is not even listed here because they were not flying yet. That's Stokes Aerospace, and they are presentations here and there, but most of the publicity happened 2 weeks ago, so that's why I skipped that. Okay, so the second stage delivers the cargo to 200, 300, sometimes 400 kilometers into space. So we can see that 25% of all the costs are related to this part of the vehicle. Still, it needs an engine. Usually, this is just one engine. You don't need such huge capabilities because you are already in space, so you just need to reach orbital velocity. And this thing is the cargo here. And also fairing, this is just required to keep the atmosphere out once or until you are launching stuff. So they are ejecting it at 100 kilometers because after that there is no atmosphere, or not so much atmosphere because still you can find atoms here and there later on, but so it's not a huge mass. And still you can recover it if you are fishing it out. So, and again, solid rocket boosters, they can be useful if your engine is weak. The problem is that people can recover it, at least in the case of Space Shuttle, they were recovering it. But the problem is that still you have to put it from segments together, so it's like a steel tube with explosive material inside of it. And for example, in Europe, there is only one company which manufactures fuel for that one, so you need a really specialized material. Otherwise, from chemical point of view, this is quite similar to thermite. What they are burning there, just obviously it's not that simple. But still it's quite expensive, so it's $3 million for each of these segments, and usually you need them in pairs. Okay, so what kind of engines do we have here? I was able to find these statistics and prices as well. So we can see that, okay, what is available now and what is under development. So what is available nowadays? Merlin 1. So this is SpaceX Falcon 9's well-proven engine, which we know that it can land a lot. So that's why we can see that what is the price here. So according to official data or press releases or interviews and so on, I was able to dig up this $2 million price. Okay, so it's quite cheap. But the problem is that obviously you need 9 of them, that's why it's Falcon 9. And also on the top, the second stage requires also an additional 1, so you need 10 of these engines to build something. Also, you need a lot of fuel, so all of this will be kerosene, just not what you can put in the jet engines. It's a rocket version of kerosene. It doesn't matter, so it's liquid fuel. So, and also probability of rapid unscheduled disassembly, so RUD, in the next 1, 2, 3, 4, 5 years, it's really low because already this is a proven technology, so it's just 1.4%. And you don't need any kind of solid rocket boosters because already this is they never used one because they wanted to be cost competitive. And can it land propulsively? Yes, it can, because we were able to see it more than 160 times, so yes, it can. And time to mass production, it's already available on the market. My personal opinion is that if Arianespace or ESA would like to improve their efficiency, the best option would be to get a license to manufacture Merlin 1D in Europe and not to deal with this one, because right now they are trying to improve their Vulcan engine, so that's why it's 2.1, but it's using hydrogen, which I mentioned that it's already operating at really low temperatures, so we are talking about minus 200 or under minus 200 Celsius. And okay, you need one of them, so okay, it's a powerful one. Just the problem is that right now it's not able to land. Okay, they are saying that it will be, so in the case study we are assuming that okay, it can do it, so doesn't matter, just in reality it's not able to do that. Fuel requirements is really low in tonnage, because hydrogen it's just 1 proton and 1 electron, so it's, the molecular mass is really small, so that's why the weight, total weight will be also really small. But since it's not a proven engine, or at least, okay, it's an upgraded version of a proven engine, just with a lot of 3D printing here and there, or additive manufacturing here and there, so that's why the probabilities of destruction is bigger. But there is a learning curve, so after 5 years we are able to be close to the Merlin 1D engine. And also you need solid rocket boosters. And we can see that, okay, mass production here is way lower than at the level of SpaceX, but still we can see that it's manufactured, so it's already happening. Okay. In the past, if you needed a steady supply of engines, you were able to go to Russia, and this is where you can get this MK 33 or Rocketdyne 180. Rocketdyne 180 is the US name of the same engine, but both of them are manufactured in Russia. And that's why they are quite reliable. They are also using kerosene, and probably it can land. So I was able to see some speculations, some people were simulating it, so probably you can throttle it down and to land with it. Just right now, because of sanctions, it's not available, but we are skipping this part from the simulation. The SCE200, it's a new project, and we can see that sooner or later it will be used by the Indian Space Program, because practically this will be the engine of the rocket which will launch people into space, so it's supposed to be much more reliable. Well, their engines were already reliable, but I don't know why, but it will be exchanged to this one. And according to rumors, it can land propulsively as well. And in real life, mass production will start in a year. In the case study, we can use it immediately if somebody would like to use this. In my sample case study, I will use this engine because I would like to test its capability. But obviously, there is still again the learning curve, so exposure. And if someone would like to experiment, then okay, Raptor 2, we can say it's under development because nothing was flying with Raptor 2 at all. So just on the other hand, we can see that they are manufacturing it in huge masses because already under Starship Heavy, so under the first stage of Starship, they were able to ignite 31 of them. Originally, they wanted 33 to ignite. Last week, at a steady fire test, just 2 of them were canceling their job because the onboard computer was thinking that they are not behaving well, so they were shut down. But we can see that these engines, there's already a Raptor 2 version, so they were able to test the first version a lot on brake pads. Also, they were using it to launch and recover the second stage, so that's the Starship part 2 years ago. So it's operating quite well, and it's manufactured by SpaceX, so maybe it's available. And the estimated price is $1 million for it. So it's usually groups are preferring this engine because it's also operating with methane, which creates less pollution into the engine, so you can reuse it way easier. It's also relatively cheap, but it's also gaseous material. So once you can find some videos that if this engine is started up, then a lot of natural gas is coming out, and once they are starting to burn, then flames everywhere. And also if they are shutting it down, that's also a lot of flames here and there after that, so don't stand around it once people are using this. Okay, fuel requirement is the same, so that's why probability of rapid unscheduled disassembly, it's relatively low. And you don't need solid rocket boosters. So, and also, it can land propulsively because we were able to see that one of the Starships was able to, okay, before of that we were able to see nice explosions, but during the tests, flight tests, we were able to see that they were able to recover. So, yeah. This is a Merlin 1D. Just I would like to show you the picture, not just talking about engines. So, Merlin 1D is not that efficient because there is the turbo pump and it's burning some of their fuel to run and to push fuel and oxidizer into the main burning chamber. So some of the fuel is just wasted for this generation. So it's not that efficient. This one is the Vulcain hydrogen engine. It has these circles because they are running through hydrogen, liquid hydrogen, through the engine bell, and after that it goes back to the burning chamber. In this case, they can cool down this thing, not to let it boil and melt. Okay, this is the Russian engine. Yeah, this is the SCA 200. I was able to find only this picture on the internet. And the difference between the Raptor 1 and the 2 versions, so we can see that it contains less amount of tubes and pipes and I don't know. So it's looks much more refined than the first version. Okay, SRB. So I mentioned already that it's burning something which is called HTPB, aluminium and AP. I don't know what is this, but it's burning like hell. And the problem is that it's burning like hell. So once it's ignited, you cannot stop this. And that's why it's nearly impossible to steer. And it's providing instantaneous torque. So it means that it's running at 100% immediately. So the G forces can be quite high, and it's also quite dangerous. So at least liquid fueled engines, you can shut it down if you are able to see that things are not going well. In this case, it will burn, doesn't matter what. And Northrop Grumman tried to build a rocket. Oh my god. So the entire thing was just a solid first stage, and they were expecting that it will be cheap. But yeah, so this is what happened when they tried the first time. So you can see that it was strapped down, so it was a static fire test. And there were some explosions. And after that it was still performing happily. Just after that the US Air Force told them that we don't need this. So even for the US Air Force it was too risky to use it for anything, because if it's doing this at the pad or near anywhere the pad, then you have to rebuild half of the Cape Canaveral. Okay, propellant. So I mentioned already that we have 3 different propellants. Practically the prices are quite the same. So, okay, kerosene is way cheaper than liquid hydrogen. Liquid methane is somewhere in between them. And also I mentioned that, okay, it requires a lot of pressure and it can be kept at low temperature. Liquid methane is somewhere between. And also you need a lot of the fuel, because mostly so everything is operating at really high temperatures in rocket engines, and you have to keep the metal components cool, especially because most of the components are manufactured from copper, so not from titanium or other fancy stuff. Copper, which is melting, so to keep everything stable, usually they are doing the trick that they are running everything at fuel rich. So they are pumping in a lot of fuel which is not able to burn up because no oxygen is added around all the components which are metal. So that's why you are using much more propellant than you're supposed to use other ways. So, yeah. And rocket body. So, usually people are reasonable at using aluminium and lithium alloy because it's, as you can see, it's relatively cheap. So 18 million US dollar or euro. In the case of carbon composite, I was looking for different data, but whenever I was looking, sooner or later the same price is coming back again and again. So yeah, it's like it's making a Ferrari for rockets. So I was not able to find the reason why it can be cost competitive, and maybe this is the only case or reason why Etherback is using it only, and now also Firefly, but yeah. Otherwise it's rigid and durable, just yeah. And reusability. So partial lipid reusability is when we're just focusing on first stage, and there is some inspection period now. SpaceX is less than or around a month, not 2 months anymore, and also fairing can be recollected, but that's all. So not second generation reusability, because still we are not able to see this. If SpaceX can launch and recover Starship, so the second stage, which is the spaceship thingy, and the first stage, which is the enormous thingy part, then we will see this they are launching it in this year, or must yesterday promoted that they will launch it within a month. Just okay, Elon time is different than usual time, so we would like to do something like this. That okay, first stage, and we can recover 70% of our costs. Or sometimes not. So that's why there is also a learning curve. So at the first year, a lot of explosion will happen, and after that it's going down. So we can reduce our probability. Yeah, that was a really sad thing, because everything happened successfully, just one leg was collapsing after landing. So you can see that, oh, it's landed, and then it's nope. Or yes, it happened also once that so this grilling thing called I forget the name. Okay, whatever. So this is what guides the vehicle when it's coming back, and it was stuck in this way. And after that, it was falling back into the sea, and after that they were able to fish it out. Just that was a sad moment. Okay, so potential market. Okay, we start in 2022, and after that we have the chance to operate until 2017. And if the price of the launch costs are above 80 million euros, then we have these sad numbers with blue. If we are able to go in the range between 60 to 79 million, then it will increasing. And if we are able to go to SpaceX levels or Falcon 9 levels, then it will jump into the sky. Obviously, we are limited that ESA has only one launch platform in French Guiana, in northern Latin America, in Kourou, so that's why we are limited in 52 launches per year, because usually you need a week to prepare a launch pad to launch something, so we are not able to reach 80, just 52. Okay, so what are the tasks for next week? When we will start our work on design, so we have to see that how we would like to combine the available engines with the available hulls, engine or rocket bodies, and also what are our margins, how the profitability and also the probability of success will happen. And also after that we will go through that we have to build all these things into the profit and loss statement and balance sheet. And also we need to realize that what are the funding costs. So how much money do we have to collect to cover this kind of development and operations. And after that we will define the value of the company and also the sensitivity towards exchange rate changes and interest rate changes. And yeah, So these are the tasks in front of us. So that's all for the semester. And don't be afraid. So this is highly. So it's a funny market because we can see immediately when things are failing, because yeah, they are going kaboom. But on the other hand, we can control all the expenditures. So this is why I was chosen this. So in the past, we were working with a company which was pulling trains, and we were able to get all the expenditures as well. But here, the design is quite simple. We can identify the relevant expenditures. We can build them in. We can simulate what is happening here and there. Also, we can have nice probabilities for the success, and that's why I like this case study so much, because it's funny, and it's also the market is constantly changing. So every week can provide us nice success or failures. Okay, do you have any question? No. Then next week we will start to build something, and after that you can build your own, and after that we will test the success, and also we will see not just the value but also probability of default of the company, so how it will change. Because first we will see that, okay, how the baseline scenario is valued in, so what is the actual potential value of Arianespace nowadays, and also what is the probability of default of this company, and after that we will see that